In this video, we'll be talking about how to use conjugate pairs to help with finding zeros and factoring polynomial equations and functions. So it's not too hard to see, and our experience with the square root has told us that complex zeros must always occur in conjugate pairs. The reason for this is sort of simple. For instance, if we were to do this example, x to the fourth minus 16, we can factor that as a difference of squares as x squared minus 4 and x squared plus 4, which then would give us, here we can factor this as x plus 2, x minus 2. But this one, if you actually solve it out and find the zeros, you'll get that it's x plus 2i and x minus 2i. And so you see here that they actually come as conjugate pairs. That is, if f is a polynomial function with real, this is important, real coefficients as we see up here, namely there's no i's floating around at first, and a plus bi is a 0 with b not equal 0, which means that in other words, I is definitely appearing somewhere in there, then the complex conjugate a minus bi is also a 0 of the function. So for example, let's find a fourth degree polynomial function with real coefficients that has -1, -1, and 3i as zeros. Again, this is a repeated 0 is the way we understand that. So for our solution, we know that x plus 1 needs to be counted twice, and x minus 3i needs to be a factor as well. But in order to have real coefficients, we would need positive 3i to be a 0, negative 3i to be a 0 as well. In other words, x plus 3i would need to be a factor, because otherwise we won't get real coefficients. So putting these two together, we would have x squared plus 2x plus 1. Putting these two together, we would have x squared plus 9. If you FOIL that out, you can see that, but it's not too hard to see based on talk about complex conjugates and such that we've done in the past. Here, if we go ahead and we put these two together, then we would have x to the fourth plus 3x cubed plus 9x squared, and 1x squared would be 10x squared, plus 9, and you would have 9 and 2 is 18x, and then plus 9. So that should be the polynomial. Of course, before we move on, it's important to realize that it said a fourth degree polynomial. What would be another one? Well, we can multiply this by any constant and we would still get another fourth degree polynomial function with real coefficients, right? As long as what we multiplied by was a real number. So now it's time to have you try an example. Go ahead and find a fourth degree polynomial function f with real coefficients that has 2, -2, and -7i as zeros. On the count of 3, I'll reveal a solution. 1, 2, 3. So again, here, x plus 2 must be a factor because -2 is a 0. X minus 2 must be a factor because 2 is a 0. And then x plus 7i must be a factor because -7i is a 0. But x minus 7i will also have to be 1 because 7i needs to be a 0, since -7i was a 0 and we want real coefficients. So we go ahead and we, putting those two together gives me that, putting these two together gives me that, and then you put those together, FOIL them out, and you will get, and simplifying, you'll get that. So now let's try to find the cubic polynomial function f with real coefficients that has 2 and 1 minus I as zeros, and f of 1 equal 3. Well, starting off, this is exactly the same as the last two examples that have been done. So what do we know? We know that x minus 2 needs to be a factor, and then x minus 1 minus I needs to be a factor. But then x minus 1 plus I would need to be a factor as well because of the conjugate pairs, right? So here, now we can put these together. Putting this together, so we have x minus 2 times, and now we got to do a lot of FOILing out. So we have x squared minus x minus, because this would be minus 1 minus I, this would be minus 1 plus I. So distributing x through, x squared minus ix minus 1 times all that, so x plus 1 plus I, because it changes all the signs, and then we do positive I times all that, so plus ix minus I minus I squared. What we end up with is, so here, all of our i's should disappear. We have x squared, we have minus 2x, that takes care of that term and that term. This ix and the negative ix there and the positive ix there will cancel. Similarly, the positive I there and the negative I will cancel, and the I squared becomes a negative 1. So we have a 1 and then plus 1, so plus 2. If you use the quadratic formula on this to find the zeros, you should get 1 plus or minus I out. So be sure to go ahead and check that. Otherwise, we did something wrong. And then we need to just expand this. So then we have x minus x cubed minus 2x squared plus 2x, distributing the x through, distributing the negative 2 through, negative 2x squared plus 4x minus 4. Combine like terms, you get x cubed minus x cubed minus 2x squared and 2x squared gives minus 4x squared. 2x and 4x gives 6x, and then minus 4. Okay? But we're not actually done. I prematurely did that because we want, this is just one possibility. We want a function where f of 1 equals 3. Well, f of 1 equaling 3 would mean that when we plug in 1, we should get 3 back. In general, if we attach any constant to all of this, call it a, so we actually have a times this, so we end up with a times all this. So what is a? Well, to find a, again, we need this condition. We know that this is my f of x, so plugging f of 1 equal to 3 tells me that plugging 1 into here needs to equal 3. So a times 1 minus 4 plus 6 minus 4 should equal 3. Well, 1 minus 4 is negative 3, plus 6 is positive 3, minus that is negative 1. So we end up with a times negative 1 equals 3, which means a should equal negative 3. So our final solution is actually f of x equals negative 3 times all of this, which would be negative 3x cubed minus, plus 12x squared minus 18x plus 12. And that is our solution. And again, it's time for you to try an example. So go ahead and find the quartic, that is degree 4, polynomial function f with real coefficients that has 1, negative 2, and 2i as zeros, and also has the added condition f of negative 1 equals 10. On the count of 3, I'll reveal the solution. 1, 2, 3. So here again, we set this up as a times each of the factors we know need to be there. Foiling out and expanding, we get this. Then the question becomes, what is a? Well, again, we can solve for a using f of negative 1 equal 10. Plugging negative 1 into here gives me this. And we know that needs to equal 10. So we have a times negative 10 equals 10, so a must be negative 1, which means if we plug negative 1 back through there, we get f. Distributing it through will give me that. For more practice and working with these conjugate pairs to create polynomials, be sure to see pages 162 and 163 of the textbook and work problems 4 and 41 through 50. In our next video, we'll talk about factoring polynomial.